A very good day to our UTP supervisor, Dr. HILMI, and also our internal examiner, Dr. Hairi Raihana. My name is Chelsea Anna. My group and I will be presenting above plant design for the production of green diesel from crude palm oil for Plant Design 2 subject. These are the team members that will be presenting along with me today. They are Shafika, Shavindran, Ikwan, and Vaishnavi. This is a presentation outline which begins with introduction, heat integration, process instrumentation and control, safety and loss prevention, waste treatment, major equipment, and process economy and cost estimation.
Assalamualaikum and good morning. My name is Ikwan and I will present the first part of the first chapter, which is the project overview. The first part of the project overview is the problem statement, and the first problem statement is this year there is a contraction of crude palm oil prices, and as a matter of fact, Malaysia is the largest CPO producer in terms of productivity, and the production of CPO contributes to billions of revenue to our country in terms of tax. And the second statement is we need to taking up the challenge to use CPO as a feedstock and we can use CPO to produce a green diesel. And policy was recently released with large federal incentives provided by the government to run businesses capable of creating demand for CPO. The objectives of this particular project is to use CPO as feedstock to produce green diesel. Second is to choose and analyze process designs schemes for the production of green diesel fuel and select the most optimum and will bring the highest profitability to the company. And third, to develop a technical and economic feasibility of the production process by employing Malaysian crude palm oil feedstock. And last but not least, it is to minimize the emissions of harmful gases into the environment, such as the greenhouse gases. So what is green diesel? Green diesel is a fuel that is chemically the same as petroleum diesel fuel. And green diesel can also be considered as a renewable fuel for the future as it produces less toxic pollutants and greenhouse gases. There are four advantages by using the green diesel. First, it is produced from renewable sources, and second, it can be used in existing diesel engines. Third, it performs well in warm and cold climate, and last but not least, it also reduces the greenhouse gases emission to the surrounding. There are two raw material used for this particular project. The first material is crude palm oil. Crude palm oil is extracted from the mesocarp part of the palm oil fruit. As you can see on the slide, there is a mesocarp layer in the figure, and Malaysia also one of the largest producers in palm oil industry behind Indonesia. And the second raw material is hydrogen. It may be obtained from hydrogen manufacturing plant, and there will be also purged hydrogen from the proposed processes. As for the products, the first desired product is green diesel. Green diesel production comprises of three main reactions, which are hydrodeoxygenation, decarbonylation, and decarboxylation. And green diesel can also be considered as an alternative for conventional fuels such as crude oil, coal, and natural gas. And the second product in this proposed project is hydrogen. Hydrogen later will be generated as byproduct in the first separator, and hydrogen is also produced because it may optimize the production cost such as green diesel cost, which is very high, by reducing expenses on the raw material itself. And now I pass the floor to Shafika.
Hi, I'm Shanka and I'm going to explain a little bit about the production routes for green diesel. Here we have an unsaturated triglyceride, and of course double bond can be found in the fatty acid. So firstly, it goes through the saturation process to remove the double bond, and that requires some hydrogen, which is called hydrogenation process or hydrotreating. Next, a further hydrotreating process that takes place in the saturated triglyceride will break up this chain and will replace all the oxygen atom with hydrogen atom. From the diagram, it shows that there are three routes that can be used, which is the hydroxygenation, HDO, decarbonylation, DCO, and lastly, decarboxylation, DCO2. And for example, if we take the decarboxylation DCO2 route from the fatty acid and combine with the help of catalyst, would produce hydrocarbon, which is the green diesel. Moving on, for the process screening, two design alternatives were proposed so that we could determine the optimal pathway that achieves the objectives of this plant design while being cost-effective. In this chapter, the two design alternatives proposed at the beginning of the plant design and process screening will be addressed adequately. This preliminary stage is very important as it will determine the best approach that meets the objective of the plant design while also being the most cost-effective. The design possibilities provided for this project are shown in figures below. The table shown in the slide provides a comparison of two types of reactors, which is plug flow reactor (PFR) and trickle bed reactor. PFR is chosen among the three reactors proposed for the hydrotreating process due to its significant advantages, such as it has high conversion per unit volume and low operational and maintenance costs compared to the trickle bed reactor. Other than that, the use of catalyst. The usage of catalyst is required for hydrocracking and hydrofining. The PFR is therefore chosen since it can be used for long-term use with the catalyst. In hydrotreating processes, catalysts like cobalt molybdenum or nickel molybdenum can be used. Based on the comparisons of the two design alternatives above, design alternative 2 was selected for the plant design. This is because the technology used for the production of green diesel has higher priority of the product, which is up to 98% compared to design alternative 1, which is only at 80%. The capital and operational costs are much lower compared to design alternative 1. Other than that, resource recovered, which is the hydrogen gas, can be recovered to be sold that can generate additional profit for the plant.
Good day, I am Vaishnavi and I will explain on the chapter 2, which is heat integration process. As we can see in this slide, this is the PDF before heat integration. There are 3 coolers and 1 heater identified in the process plant. Next, this is the PDF after heat integration is applied. We can see that there are 3 coolers and 1 heat exchanger here, while the heater is not present. To achieve the PFD after heat integration, we need to conduct 5 steps shown in this slide. First, stream data is extracted from the HISIS simulation. Next, the delta T min is set to be 10 degrees Celsius, and then the pinch analysis and heat cascade are stimulated using heat software. From the stimulation, we can obtain the minimum hot and cold utility required. Next, the heat exchanger network diagram is developed to find a suitable heat integration between hot and cold stream available. Lastly, the comparison between before and after heat integration is conducted. To conclude, the hot utility is reduced by 100% while 19.98% reduced for cold utility, and this has made a total saving about 33.3% of utility requirement.
Next, I'm going to proceed with chapter 3, which is the process instrumentation and control. This chapter consists of conceptual design, P&ID diagram, and control strategy. In this slide, the general equation for the production of green diesel can be found. Crude palm oil consists of oleic acid, palmitic acid, linoleic acid, and stearic acid. Meanwhile, the green diesel comprises of NC15, NC16, NC17, and NC18. The overall mass balance for the whole process can also be seen in this slide. Obviously, the total inlet and outlet of the component is the same, which is at 45,000 kg per hour. Moving on is the mass balance in the reaction process, which takes place in the plug flow reactor. The assumption made for this reactor is for it to be based on 99% conversion, and as you can see, the percentage difference for the inlet and outlet of the reactor is 0.017%, which is very low. Finally, as you can see from the slide here, the mass balance for both manual calculation and simulation is shown, and the percentage difference for the reaction process shows that it's very low at merely 0.001%. Since the percentage differences is less than 5%, the manual calculations and preliminary material balance that have been done are verified to be accurate.
Hello everybody. For this part, this is chapter 5. I'll be explaining about the process instrumentations and control with the help of P and ID diagram. The control strategy that we use for pumps in our industry is the flow controller, where we control the flow using a flow transmitter. Now, for the compressors, however, in our project, we used the control strategy that we used was the pressure control with the help of the pressure transmitter. The strategy that we used was feedback loop. This is the plug flow reactor where the hydroheating process takes place in our industry. So some of the main controls that we use for the pressure control, the temperature control, and also the level control. Now for the coolers in our project, what we did was we used the control objective was to maintain the temperature outlet stream. So the control variable was the temperature in the outlet stream. The manipulated variable was the peak duty of the cooler, and also the strategy was feedback loop. This example of the type of controls that we use for separator. The most important controls that we need to use for separator is to maintain the pressure, the vapor pressure in the separator, to maintain the relief pressure of the separator, and also to maintain the level in the separator. And for the heat exchanger for this project, what we used was the control objective was to maintain the temperature in the outlet stream. And the control variable was the temperature in the outlet stream. The manipulated variable was the bypass valve opening, and also the strategy that we used. This was the feedback loop. And this is our overall P&ID diagram.
Moving on to chapter 7, safety and loss prevention, which is about hazard study for this project. This is the hazard study for plug flow reactor R101. So the causes for pressure, high pressure could be due to pipe blockage or failure of control valve. And the causes for low pressure could be due to failure of control valve or pipe leakage. So the proper action that should be taken are regular inspection and install high pressure relief alarm and also high pressure relief valve. And for flow parameter, the causes for high flow could be due to failure of control valve, and the causes for low flow could be due to pipe blockage or pipe leakage or failure of control valve. And for the parameter of no flow, the causes could be the mixer is not working, or the pipe is blocked or have leakage, or it could be due to pump failure as well. So the proper action that should be taken are regular inspection, frequent cleaning schedule, and also installing flow transmitter controller. So this is the hazard study for heat exchanger E101, E102, E103, and E104. For flow parameter, the causes of low flow could be due to malfunctioning of control valve or pipeline blockage or leakage. And the causes for high flow could be due to malfunctioning of control valve or high cooling flow. So the proper action that should be taken is installing flow controller and also have regular inspection and maintenance of control valve and pipeline. For pressure parameter, the causes for high pressure could be due to malfunctioning of control valve. And for low pressure, the causes could be malfunctioning of control valve as well. And the proper action that should be taken are regular inspection and maintenance of control valve, install pressure controller and high pressure alarm, and also low pressure alarm.
As you can see on the screen, this is the proposed plan layout, which is surrounded by the infill, and the plan layout has a length of 1.3 km and width of 0.9 km. In the plan, we can see the process area is separated from the non-process area. In the process area, there are all the necessary equipment that are required for the green diesel production. And as you can see, the plant is also equipped with the wastewater equipment plant, firewater tank, scheduled gas storage area, and also the HSE building. As you can see, there is also assembly area provided in the event of emergency.
And the following chapter is waste management, which is a very important chapter for our industry. So solid waste management, the main solid waste in our plant is nickel molybdenum, which is the catalyst for our plant. for the hydrolytic process. Over time, however, these catalysts tend to become deactivated due to the hydrolytic process. So we can't directly, according to Malaysian law, we can't directly dump this catalyst into the landfills because due to its toxicity, and the heavy metals may leach into the ground and also contaminate the nearby water sources. One of the way that we have found, we have suggested to manage this solid waste is through the catalyst reactivation. Catalyst reactivation is a process where it includes de-oiling, grinding, sieving, jigging to separate extremely fault catalyst from the partially fault catalyst, metal leaching, and decooking to renew the partially fault spent catalyst, and sending the heavy fault component for metal recovery. This technique helps to recover 70% of catalyst used from 95% of activity of new catalyst. So another alternative way to manage solid waste in our plant is through metal recovery. As you know, the catalysts that we use have a lot of metal content. So according to process economy, for recovering metals from the wasted hydroprocessing catalysts containing molybdenum, nickel, cobalt, vanadium, and alumina, determine metal prices, metal content, transportation costs, and purity of the recovered metals. This metal recovery can be done in two ways, which are hydrometallurgy and also pyrometallurgy. Hydrometallurgy uses acid or base where it is leached into the catalyst, and hydrometallurgy dissolves the metals. The metals are then subsequently recovered as metals, complexes, or metals that can be sold. This helps for us to get back our capital cost for catalyst. Another way of metal recovery is also known as pyrometallurgy. Pyrometallurgy separates metal using heat treatment such as roasting or smelting, melts the catalyst at high temperatures, usually with use of flux to reduce melting temperatures and strength viscosity. Now, pyrometallurgy is less preferable as it uses high heat, and that means that we need to use more power, and that will cause our capital cost to increase. So we will prefer pyrometallurgy.
For the production of green diesel from crude palm oil, two streams have been identified to be generating liquid wastes, especially the fatty acids which comprise of oleic, palmitic, stearic, lanolic, and lanolinic acids. According to Davis, these fatty acids can be found in palm oil mill effluent (POM). The Environmental Quality Sewage and Industrial Effluent Regulation 2019 forbids anybody from disposing of industrial effluent. Effluent from the production plant should comply with the standards necessary before discharging. At a reasonable cost, wastewater and residual oils may be converted into renewable fuels. The wastewater mix from the green diesel production contains water, residual oil, microorganisms, palm fiber, solid fat, and other impurities. Although the water is non-toxic, it must be properly treated before being released into the environment owing to its acidity and high biological oxygen demand. The palm oil industry relies heavily on two technologies for wastewater treatment, which are ponding systems and open digesters with ponding systems. In this slide, I will explain a little bit about the Integrated Biogas and Wastewater Treatment (IBWT), which is being developed to treat wastes like foam and FEM by using a closed anaerobic digester and storing and utilizing the biogas generated. Meanwhile, the IBWT method decreases the BOD and COD content, which may then be discharged or further refined for reuse in milling processes. The IBWT system in general comprises of numerous processes, as seen on the right. To begin, the waste is pre-treated in a succession of ponds to cool, mix the oil, and regulate the pH prior to digestive procedures. After pre-treatment, the pre-treated waste is subjected to an anaerobic digestion to yield raw biogas. There are several technologies that can be used for this purpose, including upflow anaerobic sludge fixed film, membrane anaerobic system, and continuous stir tank reactor. Both anaerobic and aerobic digestion processes result in the production of wet sludge as a byproduct. Another liquid waste identified at the plant was water from heat exchangers. According to standard PP, the water has to be below than 40 degrees before being discharged into the river. In this plant, the solvent that goes into the heat exchangers had to go through processes which involve high temperature differences, which may result in surpassing the maximum required temperature. As for that, This solvent must first be treated to get its temperature below 40 degrees. To accomplish this, the solvent will be pumped into a condenser where it will cool. As a result, the solvent always can be cooled to 35 degrees or less.
As for gas waste management, the gas waste emitted from the proposed project is carbon monoxide and carbon dioxide. This air pollutant is released in the first separator, which is V101, and it will be further separated in the second separator, V102. Therefore, the technology used to mitigate these air pollutants is by implementing the pressure swing absorption PSA technology in the first separator, where gas-to-gas separation happens under pressure. And the PSA can be used to separate the gases in a mixture because different gases are absorbed onto a given solid surface more or less strongly. So when the pressure is dropped, the gas is released or dissolved. As you can see on the screen, this is the PSA technology, which use the active carbon and zeolite as the absorbent. So the hydrogen is separated and enriched through the removal of carbon dioxide and carbon monoxide. And the active carbon in the PSA technology is used to remove the carbon dioxide and other residual hydrocarbons. And as you can see on the screen, A indicates absorption, O indicates oxygen, D is for desorption, E is for exhaust, and I is the inlet of the PSA technology. As we all know, the Malaysia government has implemented the strict policing in order to mitigate the emission of these hazardous air pollutants by introducing the environmental quality clean air regulation in 2014. And the regulation is basically stated the limitation of gas disposal to the environment according to capacity, fuel type, and monitoring period. So as you can see on the screen, there are some regulation limits that is stated in the regulations. For instance, for any solid fuel type that releases carbon monoxide, it must be at maximum 100 milligram per meter cube. That's all for me, and I will pass the floor to Shavindan for the next chapter.
The subsequent chapter is individual major equipment design, where each of us have chosen one major equipment where we should design. The major equipment that was given to me was plug flow reactor, which is R101, and this was the method design methodology for the plug flow reactor R101. So we start by major equipment selection, which the equipment that was given to me was plug flow reactor R101. The next was the selection of the most suitable type of reactor for R101, as there are multiple types of reactors. The next step was to determine the optimal operating conditions. The next step was to get data collection from the aspect IC simulation software. The following step is the determination of reactor volume, followed by reactor sizing calculation, followed by development of mechanical design for the reactor sizing data, continued with the cost estimation for R101 unit, and continued by performing technical drawing for steam reforming reactor, and also we end with standard startup and shutdown procedure for the reactor. The basis of selection of the reactor, we chose the plug flow reactor as it is very easy to maintain. It also has result in very high conversion per unit volume. It has very high efficiency. It also ensures continuous product quality, and it's very suitable for gas phase, as the main process that's going to happen in the reactor is gas phase. And the operating parameters that happen in the reactor, temperature is at 1588 degrees Celsius, pressure is at 6600 kPa, and the phase that happens is in gas phase. So next is the sample calculation, which is done for the mechanical design of the plug flow reactor. So we start off with the reactor closure thickness. The reactor closure that was chosen was a ellipsoidal reactor. which is very suitable for the high operating pressure of the reactor. The formula used was, as you can see on your right, to find the closure thickness. So the closure thickness end was calculated to be 95.74 mm. The weight of the shell, however, was calculated to be 919.22 kilonewton with given formula. The weight of the catalyst was calculated using the mass of the catalyst, also times by the gravitational force, and what we got was 48.9496 kilonewton. The weight of the fluid, however, we use a very simple formula, which is rho Vg, which is the density of the fluid times by the volume of the fluid times by the gravitational force, where we get 321.768 kilonewton. The weight of the insulation material, that we used was fiberglass, and because it's very good, it has a very good insulation properties, and which is very suitable for the hydroheating process that takes place in our plug flow reactor, which is an exothermic process which releases a lot of heat. So the insulation material is very important. The insulation material weight that we got was 5.58 kilonewton, and the total reactor weight is the sum of the weight of the shell, weight of the catalyst, weight of the fluid, and also weight of the insulation material. As you can see, we just sum it all up, and the final total weight of the reactor which we get is 125 kilonewton. This is the specification data sheet for the flow reactor. As you can see, it has all the data that is needed, which you guys can have a look through. This shows the technical drawing part of the plug flow reactor, which was done through Microsoft Visio. So partly shows the side view of the reactor. The reactor has a total height of 9.911 meters. The height of the reactor without the closures are at 8.565 meters, and the bed length of the reactor is at 7.786 meters. Furthermore, the bed diameter of the reactor is 2.654, and the reactor inner diameter is also at 2.654 meters. The nozzle that's attached to the reactor has a thickness of 0.099 meters and has a diameter of 0.156 meters. Part B shows the top view of the reactor. The reactor has an inner diameter of 2.654 meters, as I mentioned earlier, and also has an outer diameter of 2.855 meters. The nozzle diameter, however, is at 0.156 meters. Part C shows the reactor head, which is ellipsoidal. So the reactor thickness is 0.1 meters, whereas the reactor head height is at 0.465 meters, and the ellipsoidal head's inner diameter is at 2.65 meters and the outer diameter is at 2.8 meters.
I'm Vaishnavi Ravi, and the major equipment I chose is heat exchanger. It is put simple. Heat exchanger is a device used to transfer heat from one medium to another medium. In this project, the main function of heat exchanger E102 is to transfer heat from product stream, which is known as the hot stream, to the mixed feed stream, which is known as the cold stream. Important steps involved in the design of major equipment are shown in this slide. The most important step in the design process of heat exchangers within process plan occurs at the initial process design stage. At this stage, the fundamental decisions are made about the incorporation of heat recovery networks within the process, leading to the placement and specification of the heat exchangers. First is to choose the type of heat exchanger that is feasible to meet the physical conditions imposed by the process. The most appropriate and accurate design must ensure that the length, diameter, and the number of tubes used are capable of transferring the heat energy needed. The fourth step is the heat exchanger's mechanical design. The mechanical design determines its structural rigidity and ability to provide good services. The fifth step is the calculation of equipment cost. The next step is the technical drawing of the equipment, and lastly is the protocol of startup and shutdown. There are many types of heat exchangers design that is being used in the industrial application, especially to fulfill the demand of the processes. The common types of heat exchangers are double tube, shell and tube, tube in tube, and many more. Shell and tube heat exchanger is chosen to be used in this project as it is known to be the one that is widely used, as they are very versatile, convenient to maintain, and have a good resistance to high pressure and temperature. and they are considered to be very compatible to be used for the chemical processing plants. Furthermore, they are designed to bear very high temperature and pressures. In the shell and tube heat exchanger, fixed tube type is selected as it is one of the most basic and least expensive type. The tubes can be mechanically cleaned with no leakage in the shell side as there is no junctions. The disadvantage of this type is that the outside of the tube cannot be cleaned mechanically since the bundle is attached to the shell and cannot be removed. There is no provision for differential thermal expansion between the shell and tube side, but this can be avoided by installing an expansion joint on the shell side. This slide shows the sample calculation of process design, which is divided into three parts. The first part is the overall calculation, which involves the log mean temperature difference, area of the heat exchanger, number of tubes, and shell inner diameter. This slide shows the shell and tube side sample calculation. Next is the mechanical design calculation, which includes the design temperature, design pressure, material used, tube sheet thickness, and shell thickness under internal pressure. After all calculations have been performed, the parameters and calculated values are listed in the specification sheet shown in the slide. And finally, this is the technical drawing of the heat exchanger, where the section A shows the side view of the heat exchanger, section B shows the head of the heat exchanger, and section C shows the cross-sectional elevation.
Hello, this is Shafika again, and I will be explaining for my major equipment in this plant, and that is cooler. A cooler is a cool utility that is used in process plants to cool a process fluid. Cooling may be accomplished via heat exchangers. The purpose of a heat exchanger is to aid in heat transfer within a plant system by transferring heat between two or more fluids, such as liquids, vapors, and gases of varying temperatures. There are several heat exchanger designs that are utilized in industrial applications, each one customized to the process's requirements. In the case of the green diesel production plant, several criteria are considered, most notably when designing and selecting a heat exchanger, including the type of fluids, the fluid stream, and its characteristics. A U-tube heat exchanger is used mostly according to the counterflow principle. For heat transport according to the counterflow principle, hot and cold medium flow in opposing directions. As a result, heat recovery of almost 100% is achieved. Counterflow heat exchangers therefore have a very high efficiency level. Due to the bent individual tubes, a heat exchanger with U-tube bundles requires significantly less space than a straight tube heat exchanger with the same design. U-tube heat exchangers also only generate a low pressure loss during operation. The heat exchanger's design really is based on the thermodynamic notion, which is a branch of science that deals with the movement of heat energy, temperature, and it links to other forms of heat energy. To accomplish the overall design, the following techniques were followed as per below. For the operating conditions, all of the information were extracted from expert HISIS simulation. However, since the cold stream does not include it in the HISIS, the inlet and outlet temperature of the fluid was assumed to be 25 and 70 degrees Celsius. Hydrogen gas will be entering the shell side with a temperature of 771.8 degrees with a flow rate of 25,000 kg per hour, while cooling water will enter the tube side at 25 degrees Celsius. Next are the sample calculations that were done for the cooler. According to RKC Notes Chemical Engineering Design Volume 6, the logarithmic mean temperature difference was only applicable to sensible heat transfer that occurred in the true counter current flow that the project intended to proceed, whereas C Note highlighted the logarithmic mean temperature equation as follows. Referring back to the primary purpose of the fundamental design technique for designing a heat exchanger, which is to estimate the surface area needed for the specified duty based on the available temperature references. As previously stated, the general equation for the heat transfer across the surface is as follows. Next, the tube in the selected heat exchanger will be arranged in triangular. Therefore, the recommended tube pitch, which is denoted as the distance between the tube centers, is 1.25 times the tube outside the diameter. The equivalent diameter of the shell side, DE, is determined by the tube arrangement and tube pitch. Different pressure and non-pressure components are designed in the mechanical design of a heat exchanger. The mechanical design of a heat exchanger determines its structural rigidity and ability to provide acceptable service. Mechanical design is often carried out in accordance with design standards and rules. From the calculation that has been done, the thickness for the tube sheet, shell, and flat cover will be determined. In this slide can be found the sample calculation for the shell and tube side for the cooler. Detail can be referred in the report. In this slide, it shows the specification sheet for the unit where it contains the operating data, operating conditions, and the mechanical data of the equipment. The U-tube heat exchanger with an area of 39.9 meters square will be placed in horizontal orientation. Other than that, it is also noticed that the pressure drop for the shell side is 20.09 kPa, while the shell diameter is 0.344 meter. While for the tube side, the length of the tube used is 4.88 meter, and the internal and outer diameter determined were 0.001575 meter and 0.01905 meter respectively. Also, the number of tubes found to be 137 tubes. And lastly, this is my technical drawing for the equipment where it has the side, cross-sectional elevation and bonnet head as well as measurement dimensions of the equipment.
The next major equipment is cooler E103. Beginning with design methodology of cooler E103. Firstly, define duty and collect fluid physical properties. Next, decide on the type of cooler to be used. Then, cooler sizing and process calculation was performed. Next, cooler's mechanical design was designed according to TEMA. After that, the calculation of equipment cost was done. The following step was performing technical drawing for cooler. The last step was to specify cooler startup and shutdown procedures. A cooler is a cold utility used in process facilities to lower the temperature of a process fluid. Coolers may be made out of heat exchangers. In this case, a heat exchanger was chosen to act as a cooler, as heat exchangers are used in both cooling and heating processes. Looking at the P&ID, the cooler E103 is placed after the heat exchanger E102 and before the separator V101. Looking at the operating condition, the shell side inlet temperature is 1213 degrees Celsius. Meanwhile, the outlet of shell side is 100 degrees Celsius, whereas the pressure of shell side inlet is 5000 kilopascal and shell side outlet is 4500 kilopascal. Based on the high difference between the inlet and outlet temperature and also high operating pressure, a shell and tube heat exchanger was chosen to act as cooler. The type of shell and tube heat exchanger chosen was U-tube type. This is because U-tube heat exchanger has limitless thermal expansion, able to withstand high temperature and pressure, capable of withstanding thermal shock. Tubes also may be manually cleaned with removable cover as head. Besides, it is cost-effective as U-tube is the least expensive compared to other types of heat exchangers. It is also space-saving due to its bent individual tubes. However, the limitations where individual tube replacement is difficult and tube side velocity can initiate corrosion on the inside of bends. These are the operating conditions for shell side and tube side. For shell sides, the flow rate is 45,000 kg per hour. The process mixture was in vapor phase at inlet and outlet of shell side. For tube side, the flow rate is 45,000 kg per hour as well. The cooling water was in liquid phase at inlet and outlet of tube side. These are the configurations of cooler E103. The design type of this heat exchanger is U-tube. The orientation is horizontal. The number of parallel feet and tube side feet is 1. As for the material, even though the fluids on both sides of the E103 cooler are non-corrosive, but due to the high temperature, stainless steel material was chosen. The stainless steel does not rust and able to withstand high heat. Stainless steel also has a longer lifespan and require less repairs, install, and maintenance compared to other materials such as carbon steel. These are the sample calculations of cooler E103. As there are many steps to the calculation, a detailed calculation can be referred in the report. This is the specification sheet for cooler E103. This is a technical drawing of cooler E103 that was done by Microsoft Visual. A is the side view, B is the channel and removable cover, C is the cross-sectional elevation.
In this project, I was assigned cooler E104 as my major equipment. There are 6 steps in the design methodology of cooler E104. The first procedure is the selection of cooler types. It can be either shell and tube or flat heat exchanger or spiral heat exchanger. And the second procedure is all the design parameters such as pressure and temperature, heat capacity will be obtained from data on S-Pen HISIS 8.0. And the third step is to determine the mass velocities for both hot and cold stream. And after that, the overall thermal conductance will be determined from the calculated heat transfer coefficients. After calculated the overall thermal conductance, we can compute the value of number of transfer units, NTU, heat capacity, rate ratio, temperature, effectiveness, because later we need to determine the heat transfer rate, which is Q. And last but not least, the pressure drops will be determined on both streams. The basis of selection why gasket flat heat exchanger is chosen for cooler E104 is because the material of the plate itself is usually made of stainless steel or other high alloy construction such as titanium, and it is significantly less costly rather compared to those of shell and tube exchanger of similar material. And the second reason is all heat transfer areas, which is the plate in this case, are easily detached, and it is make the cleaning purposes easy. And last but not least, the specification design of the plate arrangement results in a very compact piece of equipment. Okay, so this is the simple calculation for cooler E104. First, you need to determine the mass velocities for a both stream. For instance, in the cold stream, we can do that by dividing the mass flow rates of the cold stream by the total free flow areas of the cold stream. And after doing so, we can go to the next section. And before we determine the overall thermal conductance, we need to calculate the heat transfer coefficients first. To do that, we need to have the thermal conductivity of the spring and Reynolds number, and then the Prandtl number. And after we manage to calculate the heat transfer coefficients, we can determine the overall thermal conductance. In this case, the UA is 801 watt per Kelvin. And next, the objective is to determine the heat transfer rate. So before we manage to do that, we will need to compute the value of NTU and the heat capacity rate ratio R, and the temperature effectiveness, and then we will manage to obtain the heat transfer rate. And last but not least, for pressure drop, first we need to calculate the friction factor. And for this particular project, I use the plate with the chevron configuration and with the 30-degree angle. And from the calculation, I managed to get the friction factor of 0.1336 for cold stream. And after we calculate the friction factor, we can go through with with the pressure drop calculation from this equation. As you can see on the screen, this is the specification sheet for cooler E104, and in this specification sheet, please include the operating data, the process data, and mechanical data. And for the process data, all kind of parameters is necessary, such as temperature, heat capacity, pressure, viscosity, and density. And for the mechanical data, it is because I'm using the plate heat exchanger, I need to state the dimensions, the plate dimensions, and what material it uses, and the chevron angle, and also the material used to produce the material used in the gasket. And in this case, the gasket material is silicone rubber. As for the technical drawing for cooler U04, I use Microsoft PowerPoint to draw the plate and the frame of the plate heat exchanger. And for the plate dimension, as you can see on the screen, the port diameter is 100 mm, and the corrugation of the plate is chevron, as I stated before, and the width of the plate is 460 mm, followed by the plate length, which is 1177 mm. And as for the frame dimension, the length of the frame is 2.35 meter. That's all for me. I will pass the floor to Anna for the presentation of next chapter.
Next, we will proceed to the next chapter, which is chapter 7, which involves process economic and cost estimation. Firstly, to calculate capex, we need to calculate the purchase cost of the equipment, physical plant cost, fixed capital investment, and working capital. The total capex is 5,852,953,538 ringgit, which includes the fixed capital investment and also the working capital. Next, the OPEX consists of fixed and variable operating costs. As shown in this table, the total fixed operating cost is 1,917,503,593 ringgit. Meanwhile, the variable operating cost is 836,198,059 ringgit and 40 cents, which includes the miscellaneous material, raw materials, and utilities. Total OPEX calculated is 2,753,701,653 ringgit per year. That's all from me. Now I will invite Anna to proceed with the economic evaluation. Thank you.
Economic evaluation is very important to ensure the plant will be worth of the investment or otherwise. In this section, many sophisticated economic evaluation methods are conducted to test the feasibility of this project. Below is some important assumption made for this economic evaluation. The plant life is assumed to be 20 years, where it operates for 360 days in a year. Minimum rate of return is assumed to be 10%. Sales income, operating costs, and other costs is assumed to increase by 1.5% each year. And finally, income tax is 24% of the next profit as of year 2022. First, for economic potential, as the EP3 is still in positive figure, which also means that the plant is able to generate around Rm64 million per year, which makes the plant profitable and good for investment. Next, for profitability analysis, after plotting cumulative cash flow diagram, it shows that it takes 4 years to earn back the initial investment that has been made, while the cumulative cash flow shows a positive increase, which indicates that this project is economically feasible. Next, for the net present worth, NPW, also it shows a positive value at the end of project life, which means the project is profitable. And finally, as the rate of return percentage is more than the MARR assumed, this confirms that the project is profitable and economically feasible.
As conclusion, Malaysia has practiced strict policy by introducing the industrial effluent and clean air regulations in order to mitigate any hazardous substances from being freely disposed to the environment. The total capital investment is approximately 5.9 billion ringgit. Meanwhile, the total operating cost is approximately 2.75 billion ringgit per year, and the economic potential of the plant is approximately 6.4 million ringgit after considering cost of material, utilities, and the equipment costs. And last but not least, the simple payback period is expected to start at the beginning of year 4 based on the profitability analysis conducted. And that's all from us. Thank you.